Practice now to show what these look like. Again, you want to think in 3 dimensions. And on paper and in most of the time in PowerPoint, you're not in 3 dimensions. So here's a little movie in 3 dimensions. Here you can really see that donut. So this is dx squared. See the maximum amplitude along z-axis here and down here, and the little donut in the xy plane. So this one is dx squared minus y squared. The maximum amplitudes are right directly along axis, so that allows you to distinguish it from dxy. So when it's on axis here, it's the x squared minus y squared. So moving along here, so this is x dxy. So you see that it's in that axis, but it's not directly on axis. The maximum amplitude is 45 degrees off. So the orbitals are in between the axes there. Now we're looking at one that's it has a z in it, and it looks like it's xz. So that's where our maximum amplitude is between the x and the z axes, 45 degrees off. And our last one, we have y and z here. Again, 45 degrees off axis between the y-axis and the z-axis. So hopefully these little movies will help cement in your brain what the shapes of these d orbitals are. All right, so that's d orbitals, and we're going to be mentioning d orbitals in every lecture in this, and you have to be thinking about what the shapes of the d orbitals are to talk about today's topic, which is crystal field theory. So there are 2 types of theories that you may hear of and that your book mentions: crystal field theory and ligand field theory. And like most things that you learn about in freshman chemistry, the theories were developed to explain experimental information. So there are special properties of coordination complexes. So that's where you have a transition metal in the middle, and you have ligands all around it. So you have these coordination complexes, and they have special properties. And so people wanted to try to rationalize these special properties, and they came up with these two theories. So the basic idea behind these theories is that when you place a metal ion with a particular oxidation number in the center of a coordination sphere, and you have all these ligands, these donor ligands all surrounding them, that the energy of the d orbitals is going to be altered by the position of those ligands. So it's all about the d orbitals, and the d orbitals are going to experience some influence from these ligands, these donor ligands that are surrounding the metal. So then between these 2 theories that are used to explain how these d orbitals are being affected, the crystal field theory is based on an ionic description. So it considers the ligands as negative point charges. It's a very simplified model, whereas the ligand field theory considers covalent as well as ionic aspects of coordination. It's more powerful, it's more useful, but it's also a bit more complex. And so we don't cover it in this course. And if you go on and take the first level of inorganic chemistry, which is 503, then you'll hear about this. But for this course, we're just going to talk about crystal field theory. Even though it's very much of a simplified model, it actually works very well. You can explain quite a few properties of coordination complexes just using this simplified method.